All right, let's take a look at movement of particles across the membrane. And there are two ways that particles move across the membrane. And they're very, very similar. It's just one we call a special thing, but we'll get there, okay? So diffusion and osmosis are these two ways that things can move across a membrane. And diffusion and osmosis follow some rules. The first rule is that particles or molecules will always move from an area of greater concentration to an area of lesser concentration. So if you have a high concentration over here and a low concentration over here, whatever molecule is moving is going to move from where they're high and down over to where they're low until the concentrations are equal on both sides. And by the way, that's the second rule. When the concentrations are equal on both sides, you don't get net movement of particles. And we use that word net there. Net means that there's bulk movement in one direction or the other, right? So, for example, this is net movement, where particles are moving more in one direction than they are in the other direction. In other words, you go from having a concentration gradient to dynamic equilibrium. Okay, so concentration gradient, it means there's different concentrations in two areas. One place where the concentration is high, another place where it's low. So you've got high concentration, low concentration, and it makes sense then that molecules will move downhill, right? In fact, sometimes it's called moving with the concentration gradient or down the concentration gradient. So you get this movement until they even themselves out. And when they're at that equal point, that we call dynamic equilibrium. And that word dynamic is there because these are molecules, right? Molecules never stop moving. They're always moving, right? Particularly since typically we're talking about molecules in a fluid environment. They're always moving around. So what we mean here is that for every molecule that moves in this direction, there's a molecule that's going to move back. So the way that this is usually depicted on diagrams is you have arrows moving in both directions, and the size of the arrow indicates the magnitude of the amount of movement, and the sizes of the arrows in those diagrams are usually equal. All right, so diffusion is the random movement of particles according to that first rule. So there's simple diffusion where you've got a beaker like you see here in this diagram, and you put a clump of something in it, and you don't touch it, you don't stir it, you don't agitate it, but the particles just kind of spread themselves out until they're concentrated equally everywhere. You can also, though, get diffusion across a membrane. And really tiny things, but also non-polar, non-charged things can pass across the membrane really easily that way. So you have to have tiny things like oxygen gas, carbon dioxide that can pass through. Or you can have non-polar things like sometimes small fats or small steroid hormones can pass right across that membrane. And that has to do with that structure of the plasma membrane, right? That the core of that plasma membrane is hydrophobic. And so anything that's got a charge, if that charged thing gets into that membrane, it's going to get repelled right back out because the lipid tails don't like to contact anything that has a charge, even a partial charge. So anything that's polar and large doesn't get through either. All right. Osmosis, pretty much the same thing. Okay, and that's what you're seeing here. In this case, these are little water molecules that you're seeing, and notice they're moving across the membrane in this direction until they're spread out equally. But there's a problem. Rarely do we have a situation like we see in this diagram right here, where water is the only thing that's involved in the movement here, okay? Water tends to carry dissolved solutes. Water tends to be the basis of solutions. It's the universal solvent, right? So we have to consider the impact that solutes have on the movement of water. So we've got to come up with a rule for water movement. And these U-shaped tube examples that you see here in front of you are a good way of trying to understand this problem. Okay, so we start here, right, at this U-shaped tube. It's just got water in it, and then what we do here is we dump this. Okay, C6H12O6 is glucose. So now what we have is a whole bunch of glucose molecules in here. Right now, any sane person would say, well, that's easy. Just move the glucose across that membrane. Done deal, right? The problem is that membrane is impermeable to glucose, just like the plasma membrane. Glucose is a big molecule and it can't just cross a membrane easily. Okay, so moving glucose is not an option. So glucose now is dissolved in this water. When we dissolve something in water, we have a solution, right? And when we talk solutions, we talk about concentration of the solution. But remember, concentration of the solution is solute, which is the dissolved stuff like our sugar, over solvent, right? Okay. In this case, our solvent is water. So when you're looking at this, this is a ratio now of solute to solvent. That's what concentration is. So the concentration of the solution over here is high. The concentration of this solution is low, right? Because what you have on this side is no solute at all. It's all solvent, right? So there's not even a ratio here. On the other side over here, you've got some amount of sugar to a set amount of solvent, right? So there's a couple ways you can think of this. You can think of this mathematically, right? If you think of this as a ratio or a fraction, right, and you want to decrease the amount of the fraction, right, to get the concentrations on both sides of here equal, you want to drop the concentration on this side of the U-shaped tube, right? How do you change the value of that fraction to lower it? How do we drop the value of that fraction? Do we mess with the numerator, the solute, or do we mess with the denominator? The answer, of course, is if you can increase the denominator of a fraction, what you do is actually decrease the fraction, right? And so if we add more water to that side, if we increase the amount of solvent on that side, then what you will do is decrease the concentration, and you'll get equal concentrations on both sides. So that's the math way, and a bunch of you now are completely lost going, oh my God, math, why are we bringing this in? Don't worry about it. There's a real simple solution to this. We're in the South, right? You're sitting on your Meemaw's front porch in the South in the summertime, and you love your Meemaw, right? And Meemaw brings you out a nice cool glass of sweet tea, and you love your Meemaw, but Meemaw's sweet tea is too sweet for you to drink, right? So when Meemaw's not looking, you say, hold on a second, Meemaw, I'll be right back. You grab your glass and you go into Meemaw's kitchen, and what do you do to make that tea drinkable? How is it that you take that tea that's too sweet for you to drink and you make it so that you can drink it? You guessed it. You add some water to it, right? You dilute it. That's called dilution. That's it, right? Dilution. In other words, what you're seeing here is the water is moving in this direction to dilute the most concentrated solution, right? That's why water is moving that way. So with osmosis, when we're dealing with movement of water, we have to consider that water is a solvent, and therefore we have to take into consideration the solutes too. Right now, remember I said we want to generate a rule here. We need a rule for movement, right? Because all this is really nice, but what you need is a tool to get you the right answer in the moment, right? I think we can all agree. So here's our rule. Ready? Now that we understand Meemaw's sweet tea, water always moves to the most concentrated solution. Okay. Another way of thinking of it is water always moves toward the sugar or toward the salt, right? Because usually that's what we're talking about in biology. We're talking about dissolved salts or dissolved sugars, right? So water's always moving toward the saltiest or the sweetest solution to dilute it. Okay, with that in mind, now that you understand that, let's imagine we've got some scenarios here where I've got little beakers, and in our beaker, I've got a little cell, right? And it's in a solution. So the cell in this first solution is 10% salt, and outside it's 35% salt. Which way does the water move? That's right. It moves toward the solution. So the arrow is going to be moving out, right? You got more salt outside of the cell than inside. We're applying our rule. Water moves to the salt, okay? Now, you've got another beaker here. We'll try to make this a little bigger this time. And we have a cell that's 15% salt in a solution that's 0% salt. Which way does the water move here? You guessed it. It's going to move from the solution into the cell, right? Okay, it's moving toward the most concentrated salt solution. Okay. Again, if we have a situation where we have a cell, it's sitting in a solution and it's 10% here, 10% outside. In this case, the water is moving in and out equally. So the arrows are moving both ways there. Okay, now let's look at the applications of this, right? Okay, so when you go to the hospital, you're dehydrated and you go to the hospital, do they give you an IV that has pure distilled water in it? Of course not. That would kill you. You know why? That's this scenario that you see right here, right? Your poor little cells are like this cell that's 15% salt. Water would rush into your cells at that point, your blood cells, and your blood cells would swell until they burst. And once they burst, they can't carry oxygen for you anymore, right? It's the same scenario, or not the exact same. It's the opposite of the scenario here. Everybody's got that little brother, right, who pours salt on slugs, right? And maybe you were that little brother. I don't know, but everybody knows that kid, right? Why does the slug dry out? Because you've put a salt around the slug. That salt dissolves in the slime layer around the slug. Now that slime layer is really salty, so water rushes out of the slug to dilute that salt layer, and the slug dries out. It dies. Okay, so a couple applications there. Now, plant cells are a little different, right? If I were to take a plant cell and put it into a solution of pure distilled water, it does not burst. Why doesn't it burst? Think. You guessed it. It's that cell wall. That rigid cell wall structure is enough to protect it and keep the cell from bursting open. The cell will swell up until it hits the cell wall, and that cell wall will take a lot of pressure. In fact, that pressure that plant cells get when the cell is swelled up against the cell wall is called turgor pressure, and that's how plants can actually stand up, because every single one of their cells has turgor pressure.